Hey everyone, hello, welcome to this ESS seminar. And it is my honor to introduce you Dr. Xubin Zeng. Dr. Xubin Zeng is the Agnes Horry Chair in Environment and also the Professor of Atmospheric Sciences and also the Director of the Climate Dynamics and Hydrometeorology Center at the University of Arizona. And also Dr. Zeng's research has focused on the land, atmosphere, and also ocean interface processes. And also his expertise, broadly covers like a climate modeling and also remote sensing, the hydrometeorology, and he is really a frontiers in to bridge links, between the measurement technology, the in situ satellite data into the climate model development. And also Dr. Zeng has been elected last year as a fellow of the AGU, and at the same time, he is also the fellow of MS and the fellow of the AGU. So it's kind of like I'm kind of wordless to describe. I don't know how to use numbers. Because we can always use numbers like citations, papers. So I don't think we don't need to use these like numbers to describe Dr. Zeng's achievements. But also, it is really my honor to introduce her, to introduce his seminar today. And also, it is great for you to see you today. And Dr. Zeng, are you ready to give the seminar? Okay.
Thank you.
Okay, let's welcome Dr. Zeng.
Thank you. I have been here quite a few times in the past, but to the conference center of the National Academies. This is actually my first time to visit the department, and thank you for the opportunity. Today, I'm going to talk about the clouds, precipitation, and organized convection from non-surface effects to a new satellite wind mission concept. First, try to have a broad view of our profession. The animation shows the Earth in the universe, and we can see with time how small the Earth is in the universe. And the top panel shows the most recent imagery of our galaxy from James Webb Space Telescope's near-infrared camera and mid-infrared instruments. Both instruments are led by colleagues at the University of Arizona. And the point here is, when we think of us and our Earth, it's really tiny in the universe. We cannot even see it there. But that's our beautiful home. And we have to have a better understanding of our own home. And then how do we do that? To understand the Earth system, we must have the global observing system from satellites and ground-based measurements, and supercomputers, including the newest exascale supercomputer from DOE, the Frontier, plus the Earth system models. And for Earth system models, it has gone through the evolution from the initial atmospheric model only to atmosphere land coupled model, to atmosphere land ocean coupled model, to the full Earth system model involving different components of the Earth system, and then dynamics, physics, biology, and chemistry. Of course, none of us can look at everything. So, as a part of the Earth system, today, I'm going to talk about some of our recent work related to clouds, precipitation, and organized convection, because they are key processes of the atmosphere. They strongly interact with dynamic, thermodynamic, and aerosol conditions in the atmosphere, and also coupled with land and ocean surface processes. This is the outline of my talk. You can see they are very diverse topics. So I have to explain why do I do that instead of focus on one topic. Basically, that's our research style. I mean, of course, we have quite a few different projects, group members work on those projects, but most of the time we don't have good ideas. And I would be bored. I would push my group members, look at different topics, find new ideas. Then we do the analysis and publish the papers. I mean, that's why we have very diverse publications. And here, if some of the topics are boring to you, please take a nap. I won't be bothered. And otherwise, back up and enjoy the journey with me from one area to another. The first topic is land surface effect on local afternoon rainfall. This is a very, very old and contradictory research topic ever since there was agricultural activities. In fact, the title of the news article of our publication was, "Does rain follow the plow?" Because there was all those discussions about land surface agriculture effects on precipitation. And why it's contradictory is actually pretty simple, because from the atmosphere to land, the effect is direct. If you look at the small animation there, the blue color indicates precipitation. Right after precipitation, you see the increase of soil moisture. Of course, everybody knows that, okay? That pathway is clear, but from land surface to precipitation is more complicated. And here, we do the analysis over the southern Great Plains, actually near Oklahoma, because that's the DOE arm site with lots of observations. And in the top left panel, panel A, we just show the afternoon precipitation amount versus morning soil moisture anomaly. Straightforward correlation would have correlation 0. Of course, that's pretty boring. But at the same time, our own innovation is to recognize the land surface effect on the atmosphere is modulated by large-scale convergence of water vapor. So what we did was a very simple idea. We stratified the atmospheric state into 3 regimes: low, medium, and high regimes in terms of water vapor convergence. Then suddenly, for low and high regimes, you see significant correlations, but with opposite signs. If you bring them together, you see no correlation. In reality, stratified by atmospheric condition, we do see the impact of soil moisture on local afternoon rainfall. And then next, we just expand the analysis to all other surface quantities, as summarized in table 1 there, and also highlighted on the left. Essentially, under high regime, we do see positive correlation for so-called evaporative fraction, means latent heat divided by the sum of latent and sensible heat, and for soil moisture versus the afternoon precipitation amount. For the low regime, we see more correlations, including soil temperature, 2-meter air temperature, 2-meter specific humidity. K means the convective available potential energy in the atmosphere, and also the ratio. PBLH means the boundary layer height variation with time divided by LCL means the lifting condensation level or cloud base variation with time. And the important question would be, okay, we have done the analysis over Oklahoma. I mean, is that a big deal? Is that even transferable to other regions? So we have to answer that question. And for that, we expand the analysis to global. What we found, unfortunately, just like typically in our scientific career, does not work globally. Because from our global data analysis, morning soil moisture is not strongly affected to afternoon precipitation amounts. It's a little bit disappointing, but that's part of the journey in scientific exploration. But we did not stop there. For precipitation, there are many quantities we care about. the amount, the duration, the initiation, they are all important. So next, we look at the relationship between morning soil moisture and afternoon precipitation likelihood or triggering. And we see some good results, and they are summarized in the figure. Top panel shows the results for low regime and bottom panel for high regime. And in this figure, we show the difference between afternoon precipitation probability over wetter soils versus dry soils. Therefore, the blue color indicates preferential occurrence of precipitation over wetter soils. That's the case for low regime. Well, for high regime, the red color indicates preferential occurrence of afternoon precipitation over drier soils. And so that's pretty interesting results. And then the next question would be, how do we explain those results? Of course, we have done extensive data analysis. In the end, we identify the physical pathways to explain the results, or the summarized in the figure there. Basically, under low regime, if you have wet soil, that means lower sensible heat flux and hence lower PBL height. However, the dominant effect would be wetter soil, higher latent heat, higher relative humidity, and lower lifting condensation level, LCL or CL. The net effect would be the decrease of CL minus PBL height. The physical meaning is that because of this, it's easier for an air parcel from near surface to move up due to turbulence during the day to reach the level of lifting condensation level, become condensed to form clouds and precipitation. Okay, that's the pathway for low regime wet soil. For the high regime, because there is already large-scale convergence of water vapor, so the latent heat part is not so important. The primary effect from dry soil is to have higher sensible heat flux, higher PBL height, and hence lower CL minus PBL height, and then lead to more clouds and more precipitation. Together, we explain the results and expand from a point to global scale, and that's the first topic. Before I move to the second topic, I can pause here to see if you have any questions, or do you guys want to wait until the end? Go ahead.
If you account for the larger scale forces, that is, I can have morning wet or dry soil and afternoon precipitation, but it depends on the large scale circulation, and conditional on that, it might be different.
I mean, that's essentially what we did there, because here we show the results separately for low regime in terms of water vapor, large scale convergence, and high regime. That's essentially what we are suggesting. So what we have done is consistent with what you just said. And then let me move on to the next topic. Of course, so far we talked about the precipitation over land. And over land, we are very fortunate with satellite measurements and water rain gauges. And those data are typically merged. But over ocean, what's the ground truth? You can do field campaigns to obtain ground truth, but just one day, we got a very simple idea. That's why we published this paper. We suddenly realized something everybody knows. That is, the radar over coastal region would cover both the land and the ocean. Extremely simple idea. Suddenly we realized we can use the US National Radar Network to address the precipitation over ocean versus over land. Instead of 1 month from field campaign, we use 3 years of data from gauge corrected MRMS radar estimate of precipitation. And the climatology is presented in the top panel using high quality data. For the modern data sets, they are always metadata. It's very important for everybody to pay attention to the quality flag. And here we only use high quality data. Suddenly you realize the radar coverage is far from great over Western US. You see all those gaps because we don't have any high quality data. So that's the first point. Second, if you look at the different regions, for example, over Northwest, you do see more precipitation over land. Essentially, that's on the windward side of mountains, which is very well known. You have air move up, the mountains lifted up, form clouds and precipitation. You also see more clouds along the Gulf Stream over the east part of the domain. That's also very well known. Now the question is, we want to have some better understanding of land versus ocean. So we average the results along the distance to the coastline, and the results are summarized in the bottom panel, indicated by the green line. And on average, there are more precipitation over coastal land in the US than over coastal ocean. Even though not showing figures there, this is primarily the case in winter. In summer, there is not much difference. Now with this data, we can also address, are those satellite data really as good as promoted in terms of over ocean? And for this purpose, we pick up 3 popular data sets. One is eMERGE from NASA, one is CMORPH from NOAA, and one, of course, is from your own UCI Solutions Pershing data set. And here we summarize the results in 3 metrics: the bias, mean absolute error, and correlation squared or R squared. And you can see a few key points. First, if you look at the red line between dash and the solid red line, those are the 2 versions of the NASA eMERGE data. Solid line means the final product merging with rain gauge data, while eMERGE late means the satellite data without merging with rain gauge data. Unfortunately, the big improvement from eMERGE final is from the merging with the rain gauge data. And this also makes you cautious about the quality of the data over ocean, because good performance over land is due to the use of rain gauge data. But the interesting thing is, for those 3 products, they're all merged with some kind of surface-based measurements over land. In the end, eMERGE final is the best among the 3 products using 3 metrics. But eMERGE needs improvement over ocean. For example, if you look at the panel A, the red solid line shows a pretty large positive bias over ocean. Now, if we look at the NOAA product, CMORPH, it is the best over ocean, but needs improvement over land. Okay, if you look at the panel A, you see the negative bias of the blue line. In contrast, the Pershing product is the most consistent over land and ocean. Probably they did not do as much tuning as the other 2 data sets. So that's a real strength, but it needs improvement in terms of correlation as indicated in panel C for the black line. And of course, another topic important would be this satellite product's performance for extreme precipitation. Therefore, here we show the histogram of the ratio of satellite products versus radar precipitation in percentage, indicated by color, as a function of different radar precipitation bands for the y-axis, and the distance to coastline over land and ocean is x-axis. And the x-axis number indicates the distance in kilometer. A few points there. First, all those 3 products overestimate extreme precipitation over ocean and land. And that's indicated, now you can see, by essentially the yellow to pink color for high precipitation values. And the second point is emerge final overestimates extreme precipitation over ocean more than over land, because in top panel, you see all those pinkish colors over ocean. And then Persian is the most consistent over land and ocean again, because from land to ocean, you don't see much change in color. And finally, sea morph has more underestimation for night rainfall over land than over ocean. As you can see in the bottom panel, all those bluish colors for the sea morph. And our hope, of course, through this kind of detailed analysis, we can provide some helpful suggestions to the dataset developers for the further improvement of the products. Now, before I move to the next topic, does anybody have any questions? Otherwise, I will just go ahead.
That's really interesting. Could you explain more? So the rainfall's higher right over the coastal ocean. What is the physical mechanism that leads to it being higher? I would have thought that the land, the uplift with the air coming off the ocean in some areas, like in the West Coast, would lead to like greater instability and lower pressure and trigger more rainfall. So was that for the East Coast or the West Coast, or how did that work?
You know, first, for this paper, we really did not explain why is that the case in general. We really don't know. And from data analysis, we won't be able to figure that out. So extra efforts, including modeling, would be needed. What we pointed out are just two obvious situations we know with confidence. That's why I mentioned, for example, you have more precipitation in Seattle area, because you have the air moving in, move uphill and generate precipitation. I mean, kind of people know that very well. We are saying from data, we see the same thing. In contrast, over East Coast, because of the warm Gulf Stream, particularly in winter, when you have air move from continent to the warm Gulf Stream, you are going to have more latent heat and hence more clouds and precipitation. Those are the two things we can say with confidence. But in general, we did not explain that in this study. Go ahead.
I'd like to ask a question. So, can I draw a conclusion that the difference performance between the land and ocean may largely stem from the bias correction of the gauge? So, as I said, in your graph, the Persian didn't have gauge correction, so may they have similar performance in land and ocean, but CMOF and both CMOF and the emerge have a gauge correction in the over the land, so may they naturally have the better performance. It's only made larger because of the bias correction, not the different mechanism of the land precipitation or the ocean precipitation.
You know what you said is correct. Let me just repeat. My understanding, Persian is the best in terms of consistency over land and ocean, because the Persian uses GPCP for the bias correction. That provides some consistency. In contrast, the CMOF and the emerge is actually use gauge data, and that provides different performance over land versus over ocean.
Okay, so I have another question. So, did you consider the mixed picture pixels? I mean, the mixed pixel of land and ocean together. So, I heard that in these regions they may have satellite product may have even larger bias. More than only the land and the pure land and ocean pixels.
Yeah, that's a good point in terms of the dependence on the particular regions of the results. We did not do anything further for this relatively short article. Our motivation was ask the question, do we even know over US coast? do we have more precipitation over land versus over ocean, period? I said, I don't know that answer. And that's why we did this. I mean, green line to say on average, there is more precipitation over land than over ocean, but we did not explain that. And then we looked at the overall climatology, but we did not look at the individual regions, say California coast. We did not look at that. So we are currently working with other partners, look at the atmospheric river, and there we will focus more on the west coast, but we have not done anything at this time yet. Okay, thank you guys. Let me move on. I will skip this part to save some time and then go to the next topic about low-level clouds over global ocean. Low-level clouds are very important for the climate system. For example, for geoengineering, one idea is to increase the low-level clouds, say over California coast. That would reflect more solar radiation and hence cool the surface. And in this figure, we show the climatology using the ESCAPE satellite data. In panel D, we show the low cloud fraction. And then for 3 other panels, we show the individual cloud amounts, stratocumulus clouds, SC, cumulus clouds, CU, and stratus, ST. And besides that green box over US East Coast, there are 8 other boxes. Those are 8 very well-known regions with large scale, low-level clouds. And for our understanding of low-level clouds over global ocean, 2 papers are very influential. The first paper is by Klein and Hartmann in 1993, established a strong relationship between LCF, low cloud fraction, and lower tropospheric stability in the atmosphere, LTS, computed as the potential temperature difference between 700 hectopascal and surface. And then later, Wood and Bretherton established an even stronger relationship between LCF and estimated inverting strength, or EIS. EIS is simply computed as LTS plus an additional correction. And in our group, our philosophy is always doubt, but verify of anybody's results, including our own results. So when Lauren Kartner joined my group as a master student, her task was to verify if the conclusions of those 2 influential papers are even robust. Those are the basis of our understanding of global low-level clouds. We want to make sure we are on solid grounds, and the results are surprising. And for Lauren's case, she used 3 newer data sets of cloud amounts, or now with different reanalysis products. Bottom line, results are insensitive to reanalysis, but are sensitive to the particular cloud products used. In the top row, we show cloud amount versus LTS, the lower troposphere stability. Bottom row, cloud amount versus EIS, the other parameter. And we use 3 cloud data sets, Han and Oren. That's based on the ship measurements throughout the years. It's a climatology. And then we use 2 other satellite products, ESCAPE, ISCCP, and the series satellite data. The basic conclusions is the relation between the stability and the cloud amounts are not consistent across different cloud data sets. Before I explain this statement, I try to mention in each panel, there are 2 straight lines representing the linear regression. Black line means linear regression only using 6 boxes in the previous slide by excluding the 2 boxes over North Atlantic and North Pacific. While the purple represents the use of all 8 boxes. Those are the 8 regions with low-level clouds. We do this because we essentially replot the same figure as in those 2 papers for comparison. And for example, if you look at the purple number for the top row, using 3 data sets, R square varies from 0.13 to 0.29 to 0.66. Those are all good quantity data sets, but give you very different results. Second, the LTS, LCF relation, that the cloud amount, lower stability relation in the top row is not as strong on average as claimed in Klein and Hartmann. There they are talking about correlation squared as high as more than 0.8. Third, the EIS LCF relation is not stronger on average than the LTS LCF relation as claimed in Wood and Brethren. That's really bad news because we take those as our basis of understanding. Now we are saying those results are not really as robust as claimed. Of course, we are close colleagues. We did share our paper with them, so there is no controversy whatsoever. We just want to point out the analysis was correct, nothing wrong. What's unfortunate was at the time, 93, the only available data was the old version of the data developed by Han and Oren. And now Han and Oren revised their data. The new data give different results. And the warning here is for satellite data. Say Moody's, there are 6 or 7 connections already. How about all those wonderful papers using the first version versus the 7th version? Most of them doesn't matter because those conclusions are not as powerful as those 2 papers. But the reminder is that when you draw your conclusions, is only as good as the data you use. And the data have data's own problems. All of us need to keep that in mind. That's really the powerful message I hope to particularly pass to our students. Pay attention to the data you use. And with the newer data, particularly the escape satellite data, we can also look at the relationship for individual cloud types as shown in this figure. And the conclusion is the relationship is stronger for the stratocumulus clouds only for the right column. That's the first point. And the second, the correlations are stronger with LTS than with EIS. And basically, these results are based on the climatology. I talk with our own colleagues, including those authors there. And I also agree, those are just climatology. They are important, but for the model, what's important is instantaneous relation between clouds and the environmental condition at each time step. And that's an outstanding science question. I just try to emphasize, we are currently doing that analysis right now. And I could report some other time using the Activate data. And Activate is a NASA Earth Venture suborbital mission for 5 years. Try to better understand the relationship between aerosol clouds and meteorology. The unique aspect is we have coordinated flights of more than 500 hours involving 2 aircrafts. The low-flying aircraft, the Falcon, has a suite of comprehensive instruments for meteorology, aerosols, and chemistry measurements, while the high-flying King Air has 2 instruments, the polarimeter and the high spectral resolution LiDAR, to measure aerosols and clouds, of course, plus drop sounds. And we have almost 800 drop sounds. To my knowledge, our flight hours on average is at least an order of magnitude than other field campaign flight hours. So we have valuable data there for your free use. Even more than that, we'll help you and teach you how to use our data. We are going to have our open data workshop November 7th this year. You could attend in person in Tucson or remotely. And even better, if any of your students have great ideas of using the Activate data, we might be able to provide some small support Okay, that's pretty good incentive for you to use the activate data. If you have any questions, feel free to ask me. And the bottom panel just shows the flight patterns for the 3 years of the Northwest Atlantic Ocean. So essentially, because I'm the deputy PI, I'm doing a little bit of commercial here. Now, we move on to precipitation again, this time associated with organized convection over tropical ocean and the land. In particular, we focus on the interaction between environment and the mesoscale convective system, or MCS. MCS represents clusters of thunderstorms that produce a contiguous area over 100 kilometers across and typically last longer than 6 hours. They are very important for a variety of reasons, as listed here. Just give you one example. This figure from Shoemaker and Rasmussen 2020 paper shows the MCS contribution to total annual rainfall. Obviously, you can see over many regions in the figure, the contribution varies from 50 to 90%, as indicated by the yellow to red colors. And because of the importance of MCS, GWEX, an international program, will launch a couple of new projects associated with organized convection in the near future. By the way, GWEX is a core project of the World Climate Research Program, or WCRP, and it's dedicated to understanding the energy and water cycles, as well as their interactions with the carbon cycle in the global atmosphere and the Earth and below the land surface. Because I'm co-chairing the GWEX scientific steering group, okay, I'm doing a little bit of promotion here, just let you know, GWEX includes 4 panels to organize the various international projects: the Global Atmosphere Gas Panel, Land Surface Glass, Global Observations, GDAP, and the Regional Hydroclimate Projects, GHP. And to my knowledge, I do not remember any people from UC Irvine actually involved at this moment in GWEX activities in the past. Shu Xin was the chair of GWEX SSG, but at this moment, I do not remember anybody. This is really a great program with your broad expertise. I hope some of you will want to get involved in activities, or you want to lead some projects. You are welcome to talk with me. Besides GWEX, organized convection is also emphasized in GPEX. GPEX is a global precipitation experiment. It is a new WCRP initiative, and the vision is understanding and prediction of precipitation in a changing climate to support resilience and sustainable development. I'm leading the Tiger team to write the white paper to guide the development of the science plan and implementation plan. This new initiative will be launched next year by WCRP during the Open Science Conference in Africa in October next year. The point here is this will be a new international initiative, will bring lots of interesting funding opportunities and scientific opportunities. And again, hope some of you will pay more attention and possibly get involved.
What does Tiger team mean?
The Tiger team means, WCRP appoints a small team to do the initial work as the guiding principle for the development of the actual science plan and the implementation plan. So Tiger team just means a committee writing the white paper. Now coming back to MCS, top panel shows the MCS genesis density in color and tropical cyclone tracks in red lines for a 3-month period in 2018. And the bottom panel shows the corresponding genesis locations for the same period. Even just for 3-month period, there are about 4,000 MCS tracked and identified, giving us enough numbers for statistics. And our contribution essentially is to look at relevant dynamical and thermodynamical quantities as a precondition for the occurrence of organized convection. Of course, we have done lots of analysis, but here I just share some of the interesting findings. In this figure, we use the quantity called the divergence difference between 925 and 250 hectopascal, or we say differential divergence of the y-axis. For the x-axis means the time to initiation. So negative values means the pre-MCS and positive time means after the initiation of MCS. And that small c, the leftmost column, means the background climatology. And you can see very clearly over ocean left panel, there is a big difference between pre-MCS condition and the background climatology. This means differential divergence is a good precondition for the occurrence of MCS over ocean. However, over land, unfortunately, we really cannot tell the difference. That means this quantity is not a good condition over land for the occurrence of MCS. Besides dynamical quantities, we have also looked at thermodynamical quantities. Here, just share 2 of them with you. The top panel shows the quantity moisture, or exactly it is a saturation deficit. That means the difference between saturated value and the actual water vapor integrated between 900 and 400 hectopascal. Again, you can see there is a relatively large difference between pre-MCS condition and column C. That means this is a relatively good precondition over ocean. Over land, it's useful, but not as powerful. The other quantity would be stability, or exactly computed as the difference between maximum equivalent potential temperature, theta E, in the lower troposphere minus the minimum theta E in the upper troposphere. By the way, this quantity is also closely related to K, or the convective or variable potential energy, which is typically used for convection. Again, if you look at the prediction power for the bottom left, over ocean, there is some difference between pre-MCS and column C. That's the background climatology. So there is some power, but not as high as others. And over land, you cannot tell the difference. And of course, one question you might ask is why there is a big difference between ocean and land. We actually don't know the answer. That's one of the questions from the reviewer. We are doing the revision. We still don't know the answer yet. So if any of you have a good idea, please share with us. We would appreciate. And we do not want to do the additional modeling. So we will just try to do the additional data analysis to give some possible reasons for the different behavior over ocean versus over land. But at this time, we don't have a answer. Now, let me just move on to take this opportunity to talk about the last topic, a new satellite wind mission concept to better understand organized convection environment interactions. First, European satellite IONAS already provide LiDAR wind measurements. However, LiDAR only provides a curtain of wind in one direction only. Then how do you obtain the 3D wind or the 3D distribution of horizontal wind vectors U and V? Well, through data simulation. But the question is, after data simulation, are those real analysis data actually agree with each other? In general, they do agree with each other very well, but when weather matters, they don't. To illustrate that, in this figure, we show the frequency of root mean square vector difference between two real-analyses greater than 5 meters per second. Okay, that's a big number, 5 meters per second. When precipitation is greater than 0.1 millimeter per hour, and that the frequency is indicated by the color in the figure. You can see this color indicates over many regions, this frequency is up to 30 to 50% as indicated by green to red colors. Okay, this means indeed when weather matters, real-analysis wind don't agree with each other. That means we need new mission. And then, of course, people say, besides the LiDAR wind, do we have any other measurements of wind? Yes. There is widely available feature tracking atmospheric motion vector, or AMVs, mostly at one pressure level. For example, cloud top feature tracking wind is widely available, but only one level. So the question is, can we actually retrieve 3D distribution of wind using real observations of water vapor? Not one level, but real 3D for the whole troposphere. And prior studies have done that only over polar regions. Over tropics and mid-latitudes, nobody has done that until we finish our analysis. We essentially provide the 3D wind from 60 degrees north to 60 degrees south using the water vapor data from operational NOAA satellites, NOAA 20 and Xubin NPP. Both use hyperspectral infrared sounders separated by 50 minutes. So we keep track of the movement of water vapor between 50 minutes. Then we retrieve the wind using variational methods. And the top panel shows the descending orbit of the satellites. Then we pick up a small segment of the track as indicated in the small panel. And then we show the 3D wind, our AMV, in that top-notch panel. Here, the vector indicates the horizontal wind vector U and V component as a function of pressure and latitude along the path in the small panel. And for comparison, we show the corresponding results from Era 5 real-analysis. Quantitatively, you can see our retrieved wind looks like real wind, even the vertical structure. We are not doing a quantitative comparison because Era 5 itself is not the real observation, it's real analysis. So next, we actually use the radio sound data to do the evaluation of our 1 degree resolution MVs. The location, go ahead.
Clarifying question, what was the satellite data for the water vapor that you're using to do your tracking?
Yes, there are two operational NOAA satellites. One is NOAA 20, and one is Xubin NPP.
So is it VIIRS, the VIIRS instrument? No.
NOAA, yes, NOAA 20.
VIIRS on NOAA 20.
Yeah. And I believe on Xubin, no, Xubin NPP is the first. Yeah. And the results comparison between our 1 degree MVs and the radio sound data are summarized in those two small panels. The top small panel shows the root mean square vector difference versus pressure. Our results are indicated by the blue line, and it's within the shaded area. That means that's the errors from operational geostationary MVs. And our errors are greater than the error from real-analysis compared with radio sound data. Of course, that's not surprising because real-analysis already assimilate those radio sound data. Of course, that's not surprising, okay? What's surprising, however, is the bottom small panel. We show the speed bias. From our results, the blue line is greater than the operational geostationary MVs and the real-analysis. We took quite a few months to figure out why that's the case. Finally, we figured out because of the resolution of our data. is 1 degree. Well, for geostationary, you talk about a kilometer scale. And to quantify this effect, we use the model data because observational data are not available to do sensitivity test. And the results are shown in the bottom left figure. You can see as the decrease of the grid size from 100 kilometers or 1 degree to about 7 kilometers, you see the linear decrease in magnitudes of the speed bias. Now, through this exercise, we also get new ideas on the design of the mission. That is, we have to have water vapor measurements around 10 kilometers or less, not very coarse water vapor data. So that's the benefit of spending a few months trying to explain the results. And now, imagine for the mission, if we only have passive remote sensing measurements at 7 kilometers, we can yield MVs, but can those MVs outperform the analysis? We don't have observational data. What can we do? We use the model data for the sensitivity test called the nature run. And the results are summarized in the figure as indicated by the green line. So in the green line, we compute the root mean square vector difference between the retrieved MV versus ground truth. And then we average the results for 5 regions: tropics, middle points, mid latitudes, the next 2 on both sides, and the polar region, as shown there. And then for the orange curve, essentially represents the difference between the analysis. What we can see for this case, the green lines have greater errors than the orange lines over mid-latitude and high latitudes in the Northern Hemisphere. And the bottom line is the 3D MVs from 7 kilometers water vapor tracking are unlikely to outperform the analysis. Then what do we need to do? We need to combine LiDAR and passive measurements. And then the question, can those MVs outperform the analysis? The answer is yes. Because our team has developed the first 2-stage retrieval algorithm for this purpose. Essentially, first stage, green line, based on variational methods. The second stage, based on machine learning or random forest, using small number of measurements of wind, still with uncertainty, for the bias correction. And the results are shown in the blue line. You can see across different regions, results are much better, showing the power of combining active with passive measurements. And now, that's essentially our mission concept, combining active wind LiDAR measurements with passive microwave measurements. If we do that, we would obtain the 3-dimensional distribution of horizontal wind vector UV, temperature T, humidity Q, plus aerosols. For the governing equation of the atmosphere, we would obtain 4 prognostic quantities from observation, UV, T, Q. Its impact is guaranteed to be greater than LiDAR or AMV alone. And this has been demonstrated before many times. For example, for the GPM, Global Precipitation Mission, they use active, passive, combined concepts, and the results are much more impactful than the radar or the microwave imager alone for precipitation measurements. What we are arguing here is the same idea. We need combining active with passive for 3D wind measurements. If we have all those measurements, we can imagine many impactful applications, from weather forecasting to addressing science questions to actual direct application, from local prediction to aviation, from water resources to wind energy, even for carbon monitoring. Because we need satellite CO2 and the wind measurements plus surface flux measurements to better constrain global and regional carbon monitoring for the current global negotiations. And then the last 2 questions, how do we do them? Technically, there are 2 ways. First, For the passive sounders, it could be microwave or microwave plus hyperspectral IR. And then those two sounders can be housed with the same air spacecraft as the NIDA. Then the two sounders, one pointing forward, one pointing backward, that would generate a small time difference based on geometry. Then that would be enough to do the feature tracking. The alternative idea would be to use two small satellites, one for each sounder, one ahead, one behind the NIDA. That would also give us the capability to do combine the measurements. And then this mission can be done by one country or organization, such as by US or by EU, or through international partnership between EU and US. And for the further efforts, we do need further trade analysis on architecture and also further studies on the wind retrievals. And with that, I will stop here. This slide just provides some key points for each of the topics, and I hope we still have a few minutes for any questions you might have. Thank you very much.
Thanks for very informative talk. So I have two questions related to two of the subjects you mentioned. One is related to low cloud fraction relationship with the stability. I remember Klein and Hartmann paper, they established that linkage particularly for marine stratus cloud outside North American coast and South American coast. In your analysis, you actually look at a low cloud in many different geographic locations. Could that be the reason that low cloud relationship with the stability become weaker when you look at different part of the world?
Yes, thank you. That's a good point. We did look at the results for individual locations in our paper, and this figure essentially is the same analysis as in those two papers. We want to have a fair comparison. So here we are not creating anything, same type of analysis. We do the analysis using your three different data sets. So this figure essentially is the same as what is produced in the paper. They have done other analysis as well.
Okay, great. So the other question is, you talk about the mesoscale convecting system. So that one is well understood over the land surface area, right? Like in the United States. And most of the MCS actually over them occur mostly during the summertime, like in the United States. And what you show mostly is you are focusing on ocean part of MCS. So over the ocean, do we know MCS happen more frequently in one season than the other season, or they just happen throughout the whole year?
Yeah, first, we do emphasize ocean and the land. They do occur over tropics throughout the seasons. There are seasonal variations, but they do occur throughout the seasons. And they occur very frequently. I mean, even for a 3 month period, there are 4,000 events. And of course, I have to be careful. Is that really a magic number, 4,000? No, because if you use different tracking algorithms, you are going to get different numbers. But in any case, you have thousands of cases. Because of that, within TWACS, we are thinking of launching a new project in the future if we can find particular energetic leaders who want to take the initiative to do a comparison of different tracking algorithms. Because roughly speaking, all those tracking algorithms kind of agree with each other in general, but when you go to specific cases, they disagree. And we don't know all the details of all those methods. We feel have a comparison will help users better understanding different tracking algorithms. Then for algorithm developers, for them to further improve the tracking algorithm.
Great, thank you.
And the important thing about MCS is that most of the extreme events are actually caused by MCS. So it's really important. That's why we emphasize MCS. Of course, tropical cyclones are also important. For our mission, we will address both.
There's an online message from Clement. CMOF and iMerge rely on passive microwave measurements. Over ocean, we can see the emission from liquid rain drops in the microwave domain. Over land, the rain emission signal is masked by the surface emission signal. That is essentially why CMOF and iMerge perform better over ocean. Do you have any further comments?
I mean, again, I'm not an expert on that part, but I tend to agree with that. And my real concern is, you know, it's kind of interesting. For precipitation products, there are many other products as well, and many more probably will be developed in the future, because anybody can develop something. It's not difficult to develop something. And the puzzling part is over land. Most of the products already merge with rain gauge, but they still disagree with each other. And not by small amounts, but very large amounts. We just don't know what's going on. And it's better for those teams probably check with each other. So that's one aspect. Over ocean, I mean, that's even worse, because there is no ground truth, but at the same time, that's better because that's a real reflection of the behavior of individual products, because you cannot merge with rain gauge. Now, because of that, in QX, we are having new idea about observational data sets. In the early years, there were very few observational data sets. QX as a gold standard, we would put a stamp there saying this is QX product and hence it's pretty good. Now there are many more products. We are thinking of new strategy. Instead of claiming this one is a QX product, that one is not, we feel we try to set up the criteria for all data sets, not just precipitation, all data sets. You have to meet these criteria. If you do, it's not too bad data sets. And so that's our new strategy. If any of you have any ideas, talk with me. Our community is really facing this situation. There are more and more products. People publish papers. Not all the products are the same. What can we do to inform users to make better use of different products? I'm not talking about the precipitation per se. For all products we are talking about, there are many products.
Do you have questions? Okay, there's one from Gudrun, very nice work. Yeah, let's